So when to use state diagrams, I think we've talked about this quite a bit already, and general ideas are specified here. I'm not going to read this information. You can read it on your own, and we also talked about this last week. So elements of state diagrams, right? So we can have basically right here, you know how we said that for the purposes of quick identification in your software, each use case should get a brief use case ID. Similarly, I would say that because we're trying to simulate the states, it's also possible to keep unique IDs for your states, right? So within this elevator internally, I could benefit from the identification, and my numbering is already here, but you know how the numbering is way too generic and not very descriptive. So typically, if you want to use some kind of schema for your states, you can use basically essentially a letter in front of it, right? So state 1, state 2, state 5, state 4, and state 3, right? And there could be other types of state identification, but it's advisable to essentially, you don't want to redo this too many times, so it's advisable to just provide a short and brief unique identifier to every state. So then the states can be identified briefly by these state IDs. Okay, set of events. Like we mentioned earlier, we could be having a set of events. So let's think about events or incidents that may trigger state transitions. So the events that drive these transitions, from one state to another, can be written as labels attached to these transitions. For example, if we go from standing to loading, what could be triggering that event is that essentially that we have perhaps the call button, right? We have the call button. It's not very easy to see here, but we have the call button lit, right? We have the call button lit, and that will on this specific floor where the elevator is already standing, the call button is lit, so therefore there's nothing to wait for. Go ahead and proceed to loading state, right? So then we can say that when the loading is complete, whatever that means, there are no longer, right? So we can say that loading complete, right? This could be another transition right here. I just use longer square brackets. The transitions back to the standing, which caused the doors to close. Multiple conditions or events could trigger this. For example, maximum capacity, right? The elevator could have its internal basically weight measure that decides that it's loaded already at capacities. Therefore, it may basically start beeping and just maybe, and we could perhaps use a different state here, state 6, overload, right? So in overload state, we can say that when we get to maximum capacity, we can go to overload and signal it with some beeps, or if we have some sort of display, we can lit the display and indicate that there's an overload, so the elevator cannot be moving back to its normal operation, right? So then, of course, the condition back is that there's no longer overload or no longer maximum capacity. So again, you see how thinking about different types of situations can be formalized very effectively with state diagrams. So they really provide this capacity to formalize things that are very, very important for operation of this equipment. Right? So if we didn't have the state diagram, this overload condition somewhere would be, somewhere just written down, maybe part of the description of the formal class description, and will look much less formal and would be less effective in terms of our documentation. So doing this modeling is very, very, very effective and very, very productive in terms of understanding and planning to write the code. And as you can see that if I was asked to program this class elevator, and someone was giving me this state diagram, it would be a tremendous help, because this is like a roadmap. Okay, so this is what I have to deal with. Perhaps I will provide the methods to accomplish these state transitions. I will start thinking about different conditions and things that I have to analyze before these state transitions can take place. I can start thinking about perhaps an enumeration of these states internally. Have some sort of like enumeration variable or state variable that represents those unique states, and I can have other types of implementation that basically looks and says, okay, if I'm moving down, I cannot open the doors, right? So someone could be riding the elevator and could push the button to open the doors, right? And I'm in moving state, and I'll just totally refuse that. Again, I could beep to say no, it cannot be done, right? But it's really helpful to understand in what state we're operating, right? So these are some of the examples of the events, which of course are very closely related to the transitions, because the events that we're trying to capture and analyze lead directly to state transitions or not transitions, right? So sometimes we cannot make that transition. By the way, there could be, just to remind you, is that there could be this dynamic state like moving between the floors. And the elevator has its own request lists, a list of requests, like a list of floors that were requested by the riders. And so therefore, it can periodically, basically, for instance, if we say arrived at certain floor, right? Is this important for an elevator? I think it's absolutely important, right? So arrived at certain floor could basically say that there is no such floor on this request list. So if we say arrived at certain floor, its transition may end up right back, right? So we really don't transition too far from that same state. We do arrive at a certain floor, but keep moving because that floor is not on our request list, right? But sometimes the same condition arrived at floor, which is on the request list, will the same transition will move you back to the standing state, and because this is one of your destinations and you have arrived here, right? So again, this is dynamic behavior, and so just be aware that sometimes it's possible to do this type of self-transition without leaving the state. Certain event happens, sometimes it will cause transition to a different state, sometimes it just will leave you in the same state and you continue till next event or incident or condition or signal till till so you remain in that same state till next thing happens, right? So state transitions basically, we have a set of states and we have a set of events, right? So something that we early on we mentioned, like set of events and set of states. So we can describe these two, and so then we can describe the transitions that are possible, right? So it's easy to create a nice looking forms like this, but in reality you need a bit more of a description, because these transitions do account for all kinds of conditions and things that you need to be aware of. So this is, it's nice to have very simple formal short formulas like this, but in reality they can get a little bit more complicated. And so additionally we can also specify the actions, right? So sometimes a transition or arrival at a certain state could cause an action. For instance, when we move from standing to loading, our action would be open the doors. When we move from loading to standing, it's close the doors, right? Because that action is inevitable, right? We definitely want that action to be performed. Otherwise, we would then go to a bad state. You cannot be standing with open doors. We just decided, maybe based on our functional specification, that the elevator, the normal standing elevator state, is with closed doors, and the doors open only specifically for the purpose of loading, and that's the limitation on these states. So open and closed doors is important. Likewise, standing to moving, an action is to turn on the engine that moves the motor that moves the elevator car, and so forth, right? For instance, we also could say that in going from standing to maintenance, we want to turn on maybe a maintenance light, okay, or turn off certain subsystems or whatever, right? So these are the actions. You can see that actions inside the object can be linked to state transitions, to basically to three things, right? So actions related to a state machine operation. Three types. Clearly, state transition. State transition could cause an action to be performed, or a set of actions, right? So it could be multiple actions. Then also state entry, right? State entry. We can say that upon entry into a certain state, we want these actions. And likewise, upon leaving, state leave, right? When we're leaving a certain state, we want to perform a certain action, right? So when we transition from maintenance to standing, we want the doors to be closed, and we want the maintenance light to be turned off, right? So these are the three. So this is other powerful aspect of state diagrams, that they allow to clarify, the need for actions and connection between the actions that the object, would want to get involved in or generate with respect to states and state transitions, right? So essentially, if you think about it, both entry and leave are kind of transition related. But remember, there could be multiple transitions that transfer you from one state to another state, right? So therefore, the three, state transition, state entry, and state leave, have to be, they can be differentiated, and if you say that upon entry on this into a standing state, I want the doors to be closed, you really don't care what transition took place, what took you into the standing mode. You just say, arriving at the standing state, close the doors, right? So just very simple, a rule. And when we can do things like that, those are very effective when we actually write the implementation. It's very, very helpful, right? So that's yet another set of information that we want to consider. Actions. All right, so it's time for us to move to the next room and take a break.